So welcome to the last day of the workshop. And our first speaker of the day is Jonah, who will talk to us about Neutrino Transport. Go ahead.
All right, well, thank you. So just to get this out of the way first, do I have to stand closer? Is that the problem? All right, whatever. There we go. Good. All right, so to get this out of the way, I plan to leave a lot of time for questions, so this should be a conversation. Please interrupt me at any time if you have questions. I'm trying to monitor the chat, but if not, maybe Peter or Roland can ask chat questions. I also have to flash up this legalese. Ignore it, it's not super important. So, I want to start by telling you the basic story, which I'm sure many of you know, which is, but I want to use it to set the stage for why neutrino transport is important. So this is a neutron star merger simulation. And the key thing I want to show you here is that as the neutrons, or the neutron stars get close and they inspiral towards each other, they tidally disrupt each other, and you get this material streaming off in these tidal tails here. And after the merger, you get some remnant. Some of that material becomes gravitationally unbound, some of it does not, and it accretes back onto the remnant in this disk that you see forming here. And the aftermath looks something like this on the right here, where the center thing, I've replaced the neutron star, hypermassive neutron star with a black hole. But this is basically the diagram you get. So you have in the outer region, this expanding donut of tidally disrupted material that's gravitationally unbound, very neutron rich. I'll explain what that means in more detail in a bit. And then around the black hole or other central remnant, you have an accretion disk of material. This is the stuff that was tidally disrupted that is not unbound. And sometimes it is remnants from the collapse of the hypermassive neutron star, for example. And as this accretes onto the black hole or on the remnant, it drives this hourglass shape of wind out the polar regions of the system. This hourglass, this material, I wrote neutron poor here. It's kind of a lie. It's less neutron rich than the red material, but it's still more neutron rich than symmetric. And both of these are hot neutron rich environments. That is important because of rapid neutron capture, or our process nucleosynthesis. This is the process that produces most of the heavy elements in our universe, the very heavy elements, I should say. And to explain this, I've got this figure here that you may or may not have seen this before. This is a very funny description of a periodic table. The x-axis is neutron number, the y-axis is proton number, and the color bar here is going to be abundance. And the diagonal along here, that diagonal is all of the stable elements on our periodic table that we know and love. And everything else is an unstable isotope. I'm going to let this movie go in a minute. This is from one of my simulations, although Jonah did the processing of the trace. And what we're starting with here in these abundances down here, these are in what's so-called nuclear statistical equilibrium. All the nuclear reaction rates are in equilibrium. Zach.
How do you define stable? What's the time scale?
Yeah, this is a very, very good question. So when I run this movie, I want you to keep an eye on the time here, because what you're going to see is that the time is logarithmic, and at very late times, there are going to be elements that are sort of off this diagonal line that are still decaying on the order of like millions of years. So stable here means longer than that, long enough to exist sort of naturally on Earth. So plutonium might count, but not its isotopes, for example. Unstinium does not count. Right. So we'll let this run, and after it leaves, what's going to happen is watch that again. It climbs up the bottom of this as material captures more and more neutrons, because there's a big vat of free neutrons to capture. Eventually, we run out. And at that point, we start to radioactively decay down to stability. You can see the island of stability up here. These are the actinides. Down here, this red band is lanthanide. I'll talk about that in a bit more detail in a minute. And when this radioactive decay happens, this is going to produce a lot of heat, and that heat is going to produce glow. The color of that glow is going to depend on the elements that you produce. So in particular, this orange band here, or red pink band, the third peak, and this gray band and orange band here, these produce elements that are very heavy, and they have a lot of lines, and so they're very opaque to optical light. And if you have a lot of these, because they're suppressing the shorter wavelengths, you're going to get longer wavelength emission, and you're going to get something that looks very red. If you don't have these, and you have more, say, the second R process peak, this stuff, then you're going to get a glow that's much less red and more blue, because there's less suppression of those colors. It's really an absorption effect. And by the way, these are called the lanthanides, or the rare earth peak. This is the second R process peak. This is the third R process peak. Yes.
So you have that part of the problem where they looks like there's a lot of neutrons and like moving up big.
Yeah.
As they decay and move back to stability, that's when the new elements are forming.
All of these are element formation.
Okay.
But the elements that you get at the end are the stable ones, because everything else decays.
So where exactly does the heavier elements form the process?
Well, so the extremely heavy unstable elements are formed when it's climbing along this line, which is called the neutron drift line. Then as basically you form the heaviest stuff at that point, and then it turns out that you have to be less heavy to be stable. Basically, the reason that this diagonal line is stable elements is because it basically to get the higher the atomic number, we call that like a more heavy element, but like because of the way the strong nuclear force works, you need kind of a balance of protons and neutrons. They have to be sort of equal abundance for you to have a stable element. Up to a certain max, at which point there's nothing stable anymore, except these. And the nuclear physics for why you get these up here, I don't understand very well. You'd have to ask a nuclear physicist, but these are kind of special. But basically, the stability ends here. Yes.
Maybe I missed this, but what kind of simulation is this?
So, right, very good. So what I'm going to show you later are GRMHD simulations. However, this is post-processing that's done on after a GRMHD simulation on a Lagrangian fluid packet, so-called tracer particle, that came out from my simulation. And this calculation here is called an R process reaction network. So it is essentially tracking all of the interactions, all the reaction rates that can lead you to any of these states. So a state with some abundance in each of these cells, and reactions move you through the cells, but it's not a PDE system. It's just a massive, massive ODE system.
Okay, I was gonna say, because it goes all the way to like seconds and hours and stuff.
Yes.
It's long for GRMHs.
Much too long, yes. Another question.
Oh, and piece, like specs,
Bands, what do you mean?
color.
Oh, these are selected. Oh, I'm sorry. To repeat the question is what when I say bands, like these colored pieces in the plot, what are those and why are they chosen? So the answer to that is that these are ranges in atomic number or atomic mass, your choice, on the stable elements that produce particular peaks in the abundance pattern that is resulted from nucleosynthesis. And these have names because people study them. So for example, this one, yes. There's this structure here, and it turns out this structure is very robust. We see it if we look at, for example, the structure of the pattern of elements in the sun. You have to subtract off the other sources of element production, so there's some characterization that has to go into this. But if you look at our sun, or you look at stars, other stars in the galaxy or in the universe, you can find this pattern, so-called R process pattern. And down here, this peak here is called the iron peak. This one, this is the first R process peak, second R process peak, third R process peak, and then in the middle here is the rare earth peak. They are also categorized by the kind of element they are in the periodic table. For example, these guys, the rare earth elements. Sorry, Steve. Yes, I will try. Can you see the pointer? The mouse now? Okay, great. So these guys in the middle here are the, if you look at a periodic table, it will have a label on the bottom, these radioactive elements called lanthanides. And that's these guys, the rare earth peak. And over here, well, the peak hasn't really formed for the actinides yet because you have to wait for radioactive decay. But up here at very high atomic mass, there is another peak called the actinide peak. And on the periodic table, those are the actinides. So there's a connection both with the atomic structure of the atoms that you get, as well as the structure of the patterns that are produced here. So there's like a connection with the periodic table, but there's also reasons that people look at these in particular here. Make sense? Okay, great. Peter.
Can you say something about the uncertainty of those peers?
Yes, I wish I had a slide. I should have made one. Peter asked, for those in the audience online, what can I say about the uncertainty of the reaction rates? And Peter knows the answer. I'm sure he's asking this for the edification of the others. But very few of the dots on this curve, very few of the cells in this simulation, the reaction rates or even the masses of these elements are known. So let me try to catch it on the plot. If you look at this plot, basically the low, like, I don't know, where my hand is, where the mouse cursor is, that's sort of the band of actual knowledge. But the regions very close to the neutron drip line where you're actually climbing up this periodic table are not well understood at all. And this is a very important problem as far as understanding the origin of the elements. And you can go both ways. You can learn about those materials by looking at the sky, but if you do experiments on Earth, that can inform what you know about something you see in the sky. And this is there are a lot of facilities coming online now, for example, ESRIB at Michigan State University, that are aimed at understanding these isotopes very far from stability. Okay, gonna move on. So we saw this in the sky when in 2017, when we observed a neutron star merger and a kilonova for the first time. Well, a neutron star merger for the first time. Unclear whether or not that was the first kilonova, but it's certainly the first kilonova and so far only kilonova that we've definitively tied to a neutron star merger. This is a picture. This is a composite image from the Slope and Magellan telescopes on the day of the detection. On the left is August 17th, 2017. That's the day. The blur in the middle, that's the host galaxy. And the blue dot, or greenish dot that's pointing to here, that dot is the kilonova. That's the afterglow from radioactive decay. 4 days later, it's still there, but it's red. And what this tells us is that there were at least two sites of R process enrichment from this event, one of which produced a lot of lanthanides and thus produced a late red peak. That's what you see on the right. And one of which produced fewer lanthanides, but a lot of energy, which produced this early blue-green peak that you see on the left. So to understand this event, we need to understand at least multiple sources of R process enrichment that happen in such a way that we can see both. And there's technical meaning for that, which has to do with whether they're geometrically separated or they're moving at different speeds, something like this. Because if, say, the red stuff comes out first and it's spherical, then it will just shield the blue stuff and you won't see it. So you have to have some way that they both escape in a way that you can separate them in an angle integrated way from an observation. And just to give you a sense for how this problem might go, this is going back to your question about reaction networks. Typically, this is done in several pieces. And I'm trying to give you a sense for the tools and the timescales for each of these pieces. So the in spiral neutron stars are roughly in the LIGO band for 30 seconds or so. Of that, only the last few orbits are actually done with numerical relativity. Before that, you need phenom or EOB or some other waveform model. And the relevant time scale at that last plunge is roughly the light crossing time of one of these objects, so microseconds. Afterwards, you get some secular remnant with an accretion disk around it. The accretion of that disk onto a black hole or a neutron star can drive a short gamma ray burst. Those last for order of a second or hundreds of milliseconds. But again, the relevant time scale that you have to capture is the light crossing time of the horizon, for example. So again, microseconds. And the tools here on the left, numerical relativity codes, spectre, the Einstein toolkit, etc. I'm going to talk about my code, Nooblight, in some detail here. That is one of the tools for generating models of these disks. You can do it with a full numerical relativity code if you're very patient and have a lot of compute power, but there are specialized tools for this. Afterwards, you have to, the nuclear reactions that happen here, they happen on very short time scales, but the outgoing material, the nuclear reactions drop out of equilibrium and you have to track them separately. That's when you use a reaction network, such as PRISM or Skynet. As we talked about already, the timescales for this vary dramatically. Early on, it's seconds for the shortest of these, and up to millions of years. Finally, if you want to see what this looks, and finally, each of these produces observables, right? Gravitational waves here, possibly a gamma ray burst here. Nuclear reactions, you can look for abundances in stars and the sun. And then if you want to see what the afterglow looks like in the sky, the kilonova, you need a specialized photon transport model. And there are numerical codes to do this, as well as analytic models that are less accurate. The kilonova lasts for weeks or so, and there are various specialized tools that you can use for this, such as discrete diffusion Monte Carlo, and there are codes such as SuperNu, which is Reynolds code, and Sedona, which is Dan Cason's code, for example. As an aside, I want to mention that the physics and ideas that I've just been describing may apply to other systems. For example, the collapse of massive, rapidly rotating stars. What can happen here is if the star fails to explode, you can end up with a black hole, a rotating black hole, with essentially a stellar envelope falling on it. That stellar envelope will circularize, form an accretion disk, and drive a jet. This is thought to be one possible progenitor for long gamma ray bursts. It's been suggested by some in the community as a source of our process enrichment similar to neutron stars. It's unclear whether or not this is borne out in nature, but people are talking about it. Okay, so neutrino transport is very, very important for this problem. Neutrinos are key. And the reason that neutrinos are key for this problem has to do with the fact that they are ingredients in nuclear reactions. For example, beta decay, where a neutron decays into a proton and an electron, it must also emit an electron antineutrino. What this means is that neutrinos carry around a lepton number, a conserved quantity, and they also essentially, by inverse, can move free neutron abundance. So to show you this, I've set up a little toy model here. So this is a periodic box at roughly neutron star conditions after merger, so it's hot, it's not cold. And I've put these two boxes here, one where I have more free neutrons and one where I have less. And I put a membrane so that fluid can't move, this can't mix, but neutrinos are allowed to flow freely. And the color bar bears some explanation. This is a good time to explain YE, which is an important concept here. YE is the ratio of free electrons to free neutrons. It's called the electron fraction. Sorry, free electrons to free baryons. Any baryon will do. And YE small means more neutron rich. YE large means less. YE 0.5 is roughly symmetric matter. It's like us. And if you let this go, there we go. You see that the excess and the deficit of YE, they equilibrate. This is because neutrons are carrying YE through this problem in a multidimensional way. Thus, to get this right, you have to be doing transport. And you'll notice also that the background, if you're very observant, you'll notice that the background has changed color. And that's because the radiation field itself is holding some amount of conserved lepton number. That is it doesn't come back to the gas because the whole thing comes into equilibrium. Usually I throw up this slide and say proof by intimidation, but in this crowd, I don't think that's the case. So this is just to give you a sense for the conservation law of the equation that we're solving a problem like this. This top one is the so-called radiation transport equation. Typically in this community, for historical reasons, we use the transport equation as expressed by the photon transport community, and so this is what's written here. I is intensity. It is a way of understanding the radiation phase space density function. And what I've color-coded things here. So red is geometric terms, so general relativity stuff. Blue is coupling terms. So for example, in the momentum and internal energy conservation equations, you can see this blue G nu here, that is the radiation force source term having to do with radiation coupling. Red is obviously space-time. Important here is the conservation of electron number. This is essentially what's, if you're going to be modifying it via nuclear reactions, you have to capture it somehow in the fluid dynamics as well because it can be advected. And obviously, you import toughness of space-time. I wrote down very, very simplified versions of a 3+1 split. And I'm skipping here is baryon number, for example, which is, of course, mass conservation, and magnetic flux conservation, which is important if you want to do magnetohydrodynamics. And magnetohydrodynamics is very, very important in this problem. Yes?
What's the big D? The first equation?
That, good question. That is an advective derivative in radiation space. So this d by d lambda, I'm going to flash that equation later on. It's essentially a short note for the geodesic equation.
Then what exactly are you solving for with this equation?
Sorry, Steve. The question was, what is the big D in the neutrino transport equation? So this is a typo. The bottom should also be a D. But this equation is d by d lambda here is shorthand for solving the geodesics. Sorry, what was your next question?
So looking at the first equation, what are you solving for here?
Yeah. The other question was in the transport equation, what is the independent variable to solve? Yes, it's intensity I. And intensity I depends on, because I'm going to talk about this also in more detail. Notice how there's a subscript epsilon and f. So I is a function typically as expressed by the neutrino transport community, it's a function of space, so x, y, z. Energy, that's the epsilon. In neutrinos, f for flavor, because there are multiple flavors of neutrino, and also omega, which is the direction the radiation field is traveling. We'll go into a lot more detail about that later, but that's actually very, very important. That is why transport is hard, is because it's a 7-dimensional equation. 8 if you include flavor, but it's more like a few 7-dimensional equations than an 8-dimensional equation. All right, more questions? What's going on? Hey, look, we're about to talk about it. So, why is transport hard? Transport is traditionally considered very difficult. The reason has to do with dimensional scaling. So if you think about solving a fluid equation, or even the space-time equations, BSSN, for example, you have 4 independent variables roughly. You have x, y, z, and time. And if you make a grid of evenly spaced where all the spacing is say delta x, that means the cost of doing that calculation is 1 over delta x to the 4. It's 1 over the number of grid points per axis, or 1 over the amount of resolution you want to achieve for the point. The transport equation, however, depends on 7 dimensions. And that means if you do that same scaling argument, you end up with 1 over delta x to the 7. I'm not very good at arithmetic, but as far as I understand it, 7 is bigger than 4. And what this ends up with is that as you try to get more resolution, the cost of the calculation grows much faster than if you had to get more resolution in, say, the BSSN equation. And basically, all of the way that people think about transport up till very recently has been motivated by not wanting to have to deal with that 7. Another issue with transport is that there's actually a lot of messy physics going on. So here's just a splash of some of the important interactions that people track: emission and absorption of neutrons, protons, heavy ions, annihilation, this thing called neutron Bremsstrahlung or neutrino Bremsstrahlung, which is analogous to photon Bremsstrahlung, but it's neutrinos. scattering, and you'll notice on the right here, I've got all sorts of corrections and approximations that are typically applied in these models. It's a mess. And that's not even including neutrino oscillations, which I'm going to discuss in a little bit of detail later. But suffice it to say, neutrino oscillations are impossibly hard, but they're important. And so the physics gets very complicated. This is also a good time to mention some ways that people think about transport. Keeping an eye on the chat here. Okay. The people often characterize transport by something called optical depth. And this is an experiment you probably did in college physics. You take like a slab of material, you shine light through it. At the other end of the light, at the other end of the material, there's less light. It's attenuated exponentially. The coefficient in that attenuation is tau, the so-called optical depth. And what I just described is absorption optical depth, but emission optical depth, or sorry, scattering optical depth is also a thing, and it is important in these systems. And the limits here, the tau is much, much less than 1, you're free streaming. Nothing is absorbed, nothing is scattering, you just escape. And just to hammer the intuition here, for neutrinos, the sun is optically thin. So that should give, you've heard the story like in sun maybe take 100 years for a photon escape. Not so for a neutrino. Neutrinos go right through. The other limit, when optical depth is very high, you're in the so-called diffusion limit. Things scatter or radiate there. Basically, they behave like they're in a black box. Everywhere is a black box. And so they thermalize in their environment very quickly. Those two limits, you don't need to solve transport. There are analytic approximations that are appropriate, either the diffusion equation or a cooling function. It's in the middle, where optical depth is of order 1, where transport matters, and where you have to think. And in accretion disks, which is my specialty, which is why I'm going to keep going back to it, whether or not you need to think about transport really depends. So this is a kind of heuristic about the accretion rate and the mass of the disk that forms around a remnant after neutron star merger. It turns out they're correlated with each accretion rate and the total mass. And if you're at very low accretion rates, then obviously neutrino transport doesn't matter at all. Up to about 1% of a solar mass in the disk, you get emission matters. You have an emission-dominated disk, but you don't really need to worry about absorption. So in that region, things like cooling or leakage are good approximations. Eventually, around between 1% and 10% of a solar mass, absorption turns on. That matters. This is the regime where everything is really important. And then above, say, 10% of a solar mass, and there is a limit here at about the maximum disk mass that you can get in one of these systems, if you choose your binary parameters very carefully, about 40% of a solar mass. And in that region, absorption can in fact dominate, although you can still handle some of these processes with neutrino transport and may need to. Okay. There are a zoo of possible techniques for dealing with this that I want to categorize into roughly a few categories. There is mesh-based methods. These are also called short characteristics. These are discretizing the whole 7-dimensional space. And so if you aren't very clever, these are insanely expensive. There are techniques to be clever here. For example, sparse rate with tensor networks. And I'll talk about that a little bit of detail later. And also, computing power is getting high enough that you can kind of do this. Mesh-free methods or long characteristic methods, my specialty. These are often, for reasons I'll explain, shot noise limited. But there's reasons why that's actually good, not bad. Ray tracing and Monte Carlo are examples of this. And then there's a lot of approximate methods, such as cooling, leakage, flux limit diffusion, moment closures. I'll talk about that a little bit also. And in my opinion, the best way to go forward here to navigate this trade space is a hybrid method, which is some combination of all of these in such a way that you're using the best one in every circumstance where it's appropriate. So I just wanted to go through a few of the simple approximate techniques that people use because many of you are probably familiar with them. So for example, leakage, neutrino leakage is not real transport. Instead, you apply source terms, but don't model the radiation field itself. However, those source terms are modified. It's not just emission. They come from trying to estimate the optical depth in the full system to a cell, and then modifying, say, the emission to account for reabsorption. This requires that you calculate optical depth somehow, which is not trivial. This can often be quite expensive, but you don't have to do transport. So it is potentially faster than real transport, and it's much simpler. Another method, which is very popular, is moment methods. The most popular of these being the two-moment formalism. But I'm going to characterize them I'm going to talk about the one-moment and the two-moment formalism. You can actually extend this beyond, but I think you'll get the idea. So the 0th moment is basically you evolve conserved quantities of the radiation field. 0th moment, you evolve only the energy, and you throw away all other information. Turns out that if you do this, you get a diffusion law. If you evolve both the 0th and 1st moments, you also conserve momentum, and you get something that looks like conservation of energy and momentum, which is the Euler equations minus conservation of mass. If you care about lepton number, you even get that. You get a conservation of number. That system, like the Euler equations, must be closed because you've thrown away information about the radiation field, just as when you do fluid mechanics, you've thrown away information about the particles that make up the fluid. If you use an analytic formula, as people typically do to close this, then you have truly thrown that information out. You've made a modification and you've made an approximation. If you were actually closing it with knowledge from physics, from the actual radiation field, you actually would still be solving the exact same system. But you'd be thinking about it in terms of conservation. This has a cost, though, because if you evolve things, well, if you make an approximation, this has a cost, a real cost. Because if you evolve a fluid equation, your radiation field evolves like a fluid. So, for example, this is an example that Francois put together, where if you shine two laser beams past each other, they should just go past. In vacuum anyway, they shouldn't interact and should just travel right past each other. But if you do a moment method where you do an analytic closure, the common closures people use have the effect that the fluids splash, like the lasers will splash into each other like a fluid and not continue. This is obviously wrong. And it's an example of how the moment methods can fail. As I mentioned, increased computer power has meant that short characteristics are now available as a technique if you are bold enough and have an insight allocation, for example. So, for example, on the right here, I'm showing a figure from White et al. 2023, where they evolved a laser beam, for example, around a black hole using a finite volumes discretization of full 60 momentum space. And this team is doing this on for AGN disks on supercomputers right now. So it is possible if you're willing to use like tens of thousands of GPUs. All right, there we go. Hybrid methods. So this is the thing I mentioned. One way that you can do a hybrid method, for example, the guided moments method put out by Pablo Laguna's group this year, or Francois' original paper in 2018, Ryan and Dolan's in 2020, is that you close a moment method with a real transport solution when needed, but in the limits where you don't need to do transport, you just turn off the transport solution. And this is really nice because the moment method ensures sort of continuity of solution, guarantees conservation, the nice things that we care about, but at the same time, you basically are adaptive in space where you can solve the real problem where it matters and solve an approximate problem where it's good enough. I think these are the future, and these are a really nice approach. Right, so now I'm going to talk about Monte Carlo. Yes, Zach?
Regarding these hybrid methods,
Yes.
how do you decide when to use method A, when to use method B, etc.?
Yeah, Zach asks, in the hybrid method, how do you choose how to close, and when it's appropriate to sort of switch? And I don't think this is a fully solved problem, but to give you an example of how you can do this, you can, for the easiest examples are to measure some sort of local optical depth, for example, and say, okay, I know that in this region, I'm in an optically thick regime, I'm going to switch off transport and I'm going to do diffusion. If I know I'm in an optically thick area, I switch off transport and I just do cooling. Obviously, in practice, that is much harder. Figuring out whether you're optically thick or thin is not easy. And so there are various thoughts about this. One is the Brian and Jonah's paper that I flashed a minute ago. They talk about doing this based on sort of an implicit update where they actually run particles backwards in time as an initial guess. And this has some nice properties because you can be very adaptive. You know your emissivity, so you know what directions things are going to be going. And as particles travel, you can just turn them off as soon as they get to a sufficiently high optical depth and say, okay, this region where the particles didn't reach, that's an optically thick region, this kind of thing. So you may have to be adaptive. You may have to turn on things like implicit time to make this adaptivity work, but it does seem to be quite promising. Right. So particles in Monte Carlo. So Monte Carlo methods are a core piece of these hybrid methods that I talked about. So for those of you who are like, oh, well, you told me that hybrid methods are the future, so why are you telling me about Monte Carlo? This is an ingredient of those hybrid methods, but it is also currently, I would say, the state of the art of what people are actually running in production calculations. So my code, Francois' version of spec, and I would say the White et al. Paper, those are the codes that are doing sort of production real transport. Francois and me do Monte Carlo, and the White et al. Group is doing finite volumes. So yeah, the way Monte Carlo works is you assume that your distribution function, which is another way of representing that intensity field I was describing before, is essentially a collection of delta functions. And these delta functions represent particles. The weight here is important. It's the statistical weight in treating this physical method, and it has physical meaning. It is the number of physical particles associated with some packet of delta functions in the simulation. So W is a huge number. It's like Avogadro's number on one. And these packets are often sometimes called superphotons, for example. These methods, for technical reasons, we can talk about it if you're interested, can struggle with optical depths if you're not clever, but that is overcomable. And this is a fundamentally statistical approach. This is only meaningful, as the physics is in some sense, in the integration over your distribution function. This is not normalized, but this is, you should really think of F as a PDF. And so you can only really say like how many you can't say how many particles do I have at some position in momentum. You can only say how many particles do I have between position A and position B, between momentum A and momentum B. But you can do that numerically. So for example, here is a figure that I pulled from one of my simulations, and I'm going to come back to this figure later, where these curves are histograms of particles, and the x-axis is direction, the y-axis is essentially this F. And this is for electron, neutrino, and anti. So you can actually get explicit information about what the radiation field is doing if you have a method like this. But you have to give up on thinking of it as like this is a particle. They're particles in the numerical sense, but what they really are is samples of the distribution function. And this has the implication, obviously, that the error is Poissonian. So you have a 1 over square root of n error. And this is actually why these methods are great, because 1 over the square root of n does not scale with dimension. So this method has fixed costs for the number of particles, regardless of the dimension of the problem that you're trying to solve. And so that means that Monte Carlo and particle-based methods start to win over grid-based methods when the dimension is high. And by the way, the high dimension problem, I should have mentioned this, that's typically called the curse of dimensionality. So how does this work? Well, interactions with the gas are all probabilistic. The weights, for example, are chosen at particle emission. It's kind of a free parameter in the method. You choose it to fix in a given time step to fix the accuracy, fix the number of Monte Carlo packets that are created so that the physical number of particles is as would be given by the physics, but the number of particles created is actually sort of a free parameter, and you choose the weight such that you get the number you want. And then to compute where they're going and what their energies are, you sample the emissivity as if it's a distribution function. Now, I want to mention here that in implementing a method like this, these resolution controls are quite tricky because you want to have sort of a fixed number of particles in your simulation because that's the error you want. However, as the physics changes, the emissivity changes, so you can't just keep the weight fixed. And so changing the weight as the physics changes so that the simulation kind of always produces the right number of particles, and you keep sort of on average, constant number of particles in your calculation, is a dynamic resolution control you have to implement, and it's rather heuristic. It's not like a recipe. Think of it as like resolution controls in AMR. You have to think carefully about how you want this to behave given your problem. Keep walking too far away from the receiver here. All right. Scattering and absorption are treated very similarly. It's all probabilistic, but I want to mention an important concept here, which is biasing. Basically, any interaction you have in Monte Carlo that you treat statistically, you can either enhance the probability of a given Monte Carlo packet doing this, or reduce it, so long as you play with the weights such that the physics probability is the same. And you need to do this if you want to get, you can do this for various reasons. One reason to do this is because you want to accurately sample a process that doesn't happen very frequently in nature, but you need to have it happen sufficiently frequently in your simulation that you capture it. So for example, in new light, we bias scattering positively to enhance scattering processes. What this means to play what's called a fair game, where the particles, where the physics probabilities are the same. When we scatter a particle, we don't just change its direction. We split it. It turns into two particles. And if you do this, you need to do this to get things like the angular distribution of particles that are scattered correct. So this is a test from one of our code papers where the x-axis is angle and the y-axis is the distribution of like a test problem where I have multiple kinds of scattering interactions and they each have to be biased. If you do the blue shaded region is the analytic solution that you should get. The green curve is if you don't do enough biasing. The red curve is if you do just the right amount. You can also do this in reverse, where you can say, actually, there's a process that is happening too frequently and it's causing problems, say because it's too expensive to track. This is what happens in the core of a neutron star with scattering. And to handle this, you reduce the process of scattering to undersample that physics so that you can continue to run your simulation in finite time. This is what Francois in his paper called implicit Monte Carlo. I would argue with that terminology that means something else in, well, his terminology is good, but it means something else in sort of photon transport. So you have to be aware of that. But Francois' implicit Monte Carlo, what they do is they suppress the processes that would cause their simulation to crash so that they can run successfully even in things like neutron stars. There's a price to be paid for this. To be clear, the physics is still right because you played a fair game. However, if you are undersampling that process, you may or may not miss things. And whether or not you care about that depends on what you care to get out of the calculation. In a neutron star, things are roughly thermalized. It's kind of a black box, or sorry, black body. It's probably fine, but it's something to be aware of. Another sort of small detail I want to mention is that all the interactions I've shown you so far, they were written very simply, right? You didn't see any metric terms for the most part in the, like maybe for volume elements and things like this, but there's vector quantities in there. There were no contractions. The reason for that is that I treat
1 minute.
all of the, oh my gosh. I'm running very slow. I'm sorry, I'll try to do that. Okay, good. I treat all of these in the, whoops. There. Treat all of these in the local frame where you can do things in Minkowski space, right? I move to a tetrad frame that's co-moving with fluid to process all of the matter radiation interaction. And then I go back. I also want to mention that while GR is typically scale-free, so like for a binary black hole merger, all you have to care about is the total, like the mass ratio, the total mass of the system is kind of a free parameter. Not so with neutrino physics. There's a fundamental scale which has to do with like atomic masses and neutron masses and things like this. And so you have to track two unit systems. Essentially, you have to track a unit system for the radiation field and a unit system for sort of the lab frame physics, and you have to go back and forth. Particle motion is typically evolved deterministically by the geodesic equation, and what I've written here is the null geodesic equation. And I want to make the comment here that this is typically good enough because neutrinos, while massive, their kinetic energy is typically much, much greater than their rest energy. And also, we don't actually know what the neutrino mass is. We just know it exists and is small. So there's not really a number you can put there anyway. Putting this all together, I'm going to skip this slide, but I'm going to now show you some simulations from my code Nublight, which is a GR RMHD code, Neutrino Transport, NHD for the magnetohydrodynamics, a couple of operator splitting. There's quite a lot of literature on how to do this. Nublight is built on a history of code stretching back to 2004. But let's watch some pretty movies. So, what I'm showing here, can we start? Supposed to restart. Okay, good. These are the same simulation. The left is an colloidal slice, the right is an equatorial slice. Top is zoomed in, the bottom is zoomed out, and the color bar is white. So again, purpler is more neutron rich, yellower is less neutron rich. And at the start, you have essentially a torus in hydrostatic. We started this calculation in hydrostatic equilibrium. Obviously, in a real simulation, it won't be, but it will be roughly constant entropy, constant angular momentum, specific angular momentum. And MHD instabilities, the so-called magnetorotational instability, will cause angular momentum transport and disrupt that torus and drive it to form this accretion disk, which is sort of self-similar. But you'll note, and on the bottom, you'll have seen that hourglass shape of wind getting blown out. And on the top, you can see there's this beautiful angular structure to the electron fraction of the material that's being blown out. The higher, more polar regions are lower electron fraction, and the more equatorial regions, higher electron fraction and lower electron fraction. And because we have access to the radiation field, we can learn quite a lot about the radiation. So, and what the physics is actually doing. So for example, this is a movie, this is going to take a minute to explain. The simulation is fully 3D, but what I've done here is I've actually symmetrized the output to make a movie. So the left and the right panels here are physically co-located. You should interpret them as being physically the same place, but I've split it out to plot different quantities. And the color bar is this funny arc cinch thing. That's just to be assigned log. So it's not kind of on a log scale, but 2 signs. And on the left, I'm plotting the emission minus the absorption rates of electron neutrinos, and on the right, antineutrinos. And what I want to highlight here is that at early times, you can see that things are mostly dominated by emission and absorption of electron neutrinos. Electron neutrinos are being emitted in sort of the equatorial region, the core of the disk, and absorbed at higher latitudes, so-called corona of the disk. At late times, however, as the accretion rate dies down and the disk becomes less hot, less dense, absorption turns off, and then the electron fraction in the disk becomes set by the balance of emission between the two, between electron neutrinos and their antiparticles. I should have mentioned the right side here is electron emission minus absorption of electron.
That's a question.
Yes.
So you made the simulation is just like a rotating transport.
It's a rotating black hole with an accretion disk around it. And there was no, for clarity, this particular simulation did not have a dynamic spacetime. The spacetime was fixed. If you say try to measure what that output looks like by say making an extraction surface some distance away and tracking as material passes through it, you can build a histogram of electron fraction as a function of say the latitude on the sphere. You get this beautiful linear relation where the x-axis here, this is a histogram, the x-axis is electron fraction, the y-axis is latitude. So the bottom here is the equator, the top here is the pole, not the other way around. But the lower the latitude, the lower the electron fraction. You can also run that through nucleosynthesis, going back to the R process reactions that we were talking about before, and you find, lo and behold, that the equatorial region is very neutron rich, and it produces a lot of those rare earth elements, whereas the polar region, less so. It produces fewer of them, which translates into a light curve that is but 2 light curves, one of which is blue and one of which is red. These are spectra from a radiation photon transport code post-processed on my simulation, where the x-axis here is wavelength, the y-axis is luminous flux. The curves here are just offset. The heights don't matter. I mean, the height within a curve does, but the relative heights between the curves are not. It's just to show everything on the same plot. The blue curve is the polar outflow, the red is the equatorial, And you can see that at early times, the blue curve peaks in the blue wavelengths, red curve peaks a bit later, red wavelengths. And so what this shows is that a neutron star merger disk, just the disk, produces a sufficient breadth of neutron richness in the outflow that you can actually capture both of those components of the light curve. That's not to say that these are the only components or that this is guaranteed the explanation for, say, 170817. Almost certainly it is not. We know for a fact that there are other sources of outflow in the neutron star merger, such as the tidal ejecta, the squeeze ejecta, etc. However, even the one piece of this can, in fact, produce this richness of phenomenology. And there's lots of cool science that one can do with this. For example, this is some figures from Sanjana Curtis, who is now about to be she's about to become faculty at Oregon State University, where Sanjana looked at these extremely massive disks that are like 40% of a solar mass. They come from black hole and neutron star mergers, found some very interesting phenomenology in the kinds of nuclear data that comes out, kinds of nucleosynthesis. Kelsey Lund, who just defended her PhD thesis yesterday, looked at the magnetic field strength and its impact on these systems, and for example, found this tantalizing, interesting structure where as you start with a stronger initial magnetic field, you change the amount of actinides that are synthesized in these systems. And this is really interesting because it turns out that if you look in the sky, you actually see different stars with different amounts of actinides in them. And maybe that suggests that the zoo of possible neutron star mergers, they were enriched by different systems with different magnetic field strengths, for example. Also looked at very, very late time outflow. So I extended that first simulation I just showed you up to 1.2 seconds in physical time, which is a long time. If you remember that the relevant time still here is like microseconds. And what we found is that in addition to those two components I showed you before, there's another component, which is this very late time secular, so-called viscous outflow, which is coming from conservation of angular momentum, which is also very neutron rich. And so that can sort of normalize the total abundances that you see out at the end to ensure that you basically always get the right pattern in the rare earth peak. Last thing is neutrinos can oscillate, as I mentioned, and this can impact the amount of neutron richness, because you can emit, say, an electron neutrino, it'll oscillate, and now it's not an electron neutrino anymore. So if you absorb it, you just lost that electron number. This is very important, but it's also impossible to measure from first principles because collective oscillations that happen in these hot bank systems, the relevant length scale is like centimeters. The relevant length scale of a neutron star or a black hole is kilometers. So you can imagine that that order of magnitude difference is not tracked. However, there are ways of looking for evidence of neutrino oscillations. For example, by looking at the relative angular distributions of the different neutrino flavors and trying to say whether or not there's a neutrino there, maybe building up some heuristic treatment, some good model to try to capture this. And this is something we're working on with this excellent postdoc, Hayao Mukhopadhyay, who I think is on the job market, if any of you are hiring. And she recently analyzed one of our simulations and looked for where neutrino oscillations are happening in the calculation, given this very detailed radiation transport solution. Okay, I'm going to stop here, but if you're interested, I'm just going to very quickly flash some figures of cool science that we can do with our new GPU code. I'm also going to highlight two more students. Hayao Mukhopadhyay. Is this not working? Okay, here we go. Brendan Barker, who also just defended his thesis, is starting at Los Alamos in the fall as a fellow, who's doing neutrino transport simulations like the ones I've been showing you on GPUs with our new code Phoebus. And Miriam Gagawashvili is doing supernova simulations on GPUs with Phoebus, also just defended her thesis. And just going to flash up some phone numbers here if you're interested in any of these codes. Everything we put out is open source. You're welcome to play with it. Parthenon is an adaptive mesh refinement code, similar to Amarex, I suppose. Phoebus is GRMHD built on top of Parthenon. New Blight is my older code that does neutrino transport that I was talking about. Singularity EOS and Singularity OPAC are GPU-capable microphysics libraries. EOS for equations of states, tabulated data. Singularity OPAC is for opacities and radiation source terms. The Definer is a performance portable, GPU capable, like table reader and interpolator. All right, so to summarize, neutron star mergers are very important, definitively a source of our process elements. Mapping merger parameters to observables has many uncertainties and degeneracies. Neutrinos are very important for this. Transport is very hard, and real transport has been intractable until quite recently. But I think we've hit a phase transition. Better computers and better numerical methods have converged. And in my opinion, we're not so far away from where neutrino transport of real, like transport solutions will just be routine in the same way that solving BS essentially. So future is neutrino bright. Thank you.
I'm trying to wrap my mind around the effect of on the so the source, one of the sources is the beta decay.
Yes.
Right? And another source is just heating up of the ejector when the
So if I understand correctly, I'm summarizing for the audience, the online audience. Your question is, what is the impact of the neutrino physics on nucleosynthesis? And part of what you're getting at is like, what are the important physical processes that drive neutrino interactions?
so what are the sources of neutrino, and then the neutrino will become ejector, right? So what is happening when the ejector gets to the source?
Yeah, great. So the question was, neutrinos are going to hit the outflow, like the tidal ejecta, and what is the impact of that on that ejecta? You're absolutely right that neutrinos can irradiate the outflow as it's going out and impact it as nucleosynthesis is happening. My simulations, other than the our process calculations, don't track this. They turn off before you ever get to that point. But it can have an impact. Neutrinos, if you have a source of electron neutrinos more than electron antineutrinos, which is likely because your remnant is likely deleptonizing, those electron neutrinos irradiating the outflow will typically raise the electron fraction and will suppress the more robust R process, for example. So yeah, that's quite important.
Well, neutrino oscillator, you could possibly do it, get it with 1/3 electron, 1/3 muon, 1/3 tau then.
Unclear.
What?
Unclear.
Unclear.
So what you just described is sort of like an equilibrium kind of thing, but it depends on the mass hierarchy of the neutrinos, and it also depends on the details of how neutrino collective oscillations interact with the ambient matter field. So this is an open topic of discussion. People do not know what the neutrino field is going to turn into when oscillations happen in these very fast oscillation systems. Back.
Earlier on, you showed that the table felt like the long effects of correction. So are those considered in your
Approximately. So the question for the audience is, I showed this table of neutrino interactions and I had like correction terms. Things like, and there's things like stimulated, you have stimulated emission in lasers. Neutrinos are fermions, so they also can have these kinds of processes. So something called stimulated absorption, for example, or emission blocking. Those are treated approximately. To treat those correctly, you would need to have your opacity depend on the ambient neutrino field, which is typically not done because that's quite expensive. So there's sort of like people kind of squint and estimate on how much it should matter. But one frontier in this field is trying to go beyond that. So for example, neutrino annihilation, doing this properly requires knowledge of the neutrino field, which a Monte Carlo method has. So I'm working with a postdoc who actually works on the Einstein toolkit. You might be in the audience online. Hensch is working on tracking, for example, neutrino annihilation carefully in these kinds of simulations.
No, I guess we have to stop here. So great. Thank you. reconvene in half an hour for the next session.